Good morning, everybody. Hopefully everybody can hear me loud and clear. Thank you for attending this morning's webinar from Peak Scientific. Today we are going to look at choosing the right setup for your GC system. So we're going to have a look at various aspects that you may want to consider before investing in a gas generator solution for your laboratory. So just to get things started, we'll look at the key benefits of gas generators. So the main 5 benefits that customers really consider when they look at a gas generator solution are things like convenience, so having gas on demand, no need to change out cylinders or worry about maintaining supply of stocks of cylinders. Then there is the consistency that gas generators provide, where they produce gases using a repeatable method, which means that you get a consistent gas quality 24/7. You also don't have to worry about impurities, as can be the case with cylinders, and you don't have to worry about monitoring your gas stocks, so you don't have to worry about running out of gas when you use a generator. And of course, one very important aspect that a number of customers will consider is the economy of gas generators. So once you've invested in a gas generator, the ongoing costs of ownership are very low, whereas if you are maintaining supply of cylinders, then you have a constant outlay of gas as you continue to replace one cylinder after another. So it really allows you to take hold of your lifetime costs of gas and manage that more effectively when you use a generator. And then safety is an incredibly important aspect, and I do have a few slides on this afterwards. Pressurized gas cylinders contain large quantities of gases, and it's not just gases such as hydrogen that pose a risk. There's also a risk posed by inert gases. And then when we look at the repeated deliveries, which are often by truck, then also the environment is another aspect which gas generators can help contribute towards, because once you have the generator installed at your laboratory, you're not having to have repeated deliveries, which means that we should be having fewer trucks on the road. Okay, so moving on to gas safety. Compressed gases, as I just mentioned, can be dangerous regardless of whether they are flammable gases or inert gases. So if we look at inert gases such as nitrogen, helium, argon, a rapid release of these gases would potentially result in asphyxiation because of elimination of oxygen from the laboratory environment. And then when we look at flammable gases such as hydrogen and acetylene, of course, there's the risk of fire or explosion if there's a large volume release into the laboratory. And we have to consider that a large cylinder will contain up to 9,000 litres of compressed gas. So this can significantly alter the gas composition of a laboratory space. And if you're using liquid nitrogen dewars, another thing to bear in mind is that 1 litre of liquid nitrogen, if this is spilt, will evaporate to produce almost 700 litres of nitrogen gas. So again, it's not just cylinders that pose a risk, but dewars as well. So inert gas release, as I said, can result in oxygen displacement. And the table here just shows the effect of a lowering of the oxygen concentration in an enclosed space on the people within that environment. So as soon as the volume of oxygen drops below 18%, the environment can be considered very unsafe, and as we displace more and more of that oxygen, can actually result in death. So certainly for any of you that are using dewars of liquid nitrogen, this is certainly something that you should look at. But again, considering cylinder supply, it's important to make sure that your cylinders, if you are using them, are maintained properly to prevent any rapid release of gas into the lab environment. When we look at hydrogen, again, a large cylinder will contain up to around 9,000 litres of gas at high pressure. If we contrast this with a generator, so for example, our precision SL generator, we have only around 150 cc's of gas at a much lower pressure, but the generator is capable of supplying a number of FIDs simultaneously. There's also a shift in regulation of cylinder storage, and particularly of hydrogen. So this can also be an increasing cost to laboratories, as cylinders need to be moved away from the laboratory environment. And there are also a number of hidden costs of cylinders. So it's not just the cost of the cylinder which contains the gas, but you will also be paying for delivery, for rental of cylinders, and that includes empty cylinders or standby stock. It's also the practice to replace regulators on a periodic basis. Also looking at delivery line maintenance, and the replacement of traps is also an expense that perhaps is not always considered when you're looking at the cost of cylinders in comparison to a generator. And so generators can be factored into new lab installations as well, and can give significant cost savings when we consider a number of these hidden costs associated with cylinder supply. And on the Peak website, we do actually have information on cylinder safety as well as hydrogen safety. So please visit www.peakscientific.com and have a look at the materials we have available there. And so using a hydrogen generator can be a way to improve the safety of your laboratory. So a customer of ours from the US, we have here quoted, saying that the key benefit that they've seen has been eliminating the issues of surrounding safety associated with compressed gas cylinders by shifting to generators. When we look at the hydrogen generator itself, what safety features does it have? So I mentioned before, it has a low internal volume of gas at a low pressure, but a high enough volume of gas and high enough pressure to supply a number of GCs simultaneously. The system has internal monitoring of pressure to make sure that not only is it leak-free, but also to make sure that the system pressure doesn't become too high. And in the event that anything were to go wrong in the hydrogen generator, then it has auto shutdown features for both internal leaks and external leaks. And when we start up the generator, it will perform a pressure decay test to make sure that there are no internal leaks before we supply gas to our GC. And if there was a significant issue with the production of hydrogen, we would shut down the cell to make sure that there is no risk of continuing to produce hydrogen and supply this into the lab. Okay, so that section really looked at the benefits of generators compared to cylinder and dewar supply. Now we will look at some of the steps that you may want to look at in calculating the requirements of gas for your GC. So the table At the top of the slide shows the most common detectors that we see associated with GC. Of course, there are other detectors that you may be using, but this probably covers the vast majority that we find in most labs. And we can really split the types of detector into destructive and non-destructive types. So the destructive detector types burn a flame. So this would be the FID, FPD, NPD, and SCD detectors here. And then the non-destructive types would be the ECD and TCD. The numbers give us a typical flow range that's required for each detector type of hydrogen, zero air, or nitrogen. And we have a couple of notes here on the type of gas or the gas generator type that we would normally recommend. So where you see trace, that would be a nitrogen trace. And I'll explain a little bit about that afterwards. And one point to note on the TCD is that the same gas is used as both a reference and makeup gas as for the carrier gas. So if we're looking to calculate the requirement of our detector supply, if there's no information available, then normally what we would do is just use the worst case flow rates. So taking those figures from the table, for an FID, for example, we would expect a maximum of 50 cc's per minute per detector of hydrogen. So if we had 3 FIDs, we would calculate an absolute maximum of 150 cc's per minute of hydrogen, 120 cc's per minute of nitrogen, and 1.5 litres per minute of zero air, based on the absolute maximum we would expect ever to see supplied to a detector. And if we had a mixture of detectors, again, we would just take the maximum flow rates estimated for each of the detector types and just add up the total amount of hydrogen, nitrogen, and zero air. And in this case, because we have an ECD, we would recommend nitrogen trace because this is hydrocarbon-free nitrogen, whereas for the FID, normally it's fine to use standard nitrogen, which does not have a catalyst chamber to remove hydrocarbons. However, if we do have method data available, then we can be a bit more precise in the amount of gas that we calculate for our detector supply. And all we need to do is look at the method information either on our computer, or if you have printouts of the method parameters, then you can look into where this is saved and look for the necessary information. Now, if you're not used to looking at method information, it can at first sight look confusing, but the main thing is just to pull out the key information. So I have a couple of examples here of acquisition methods. On the left, we don't have any specific flow information. We just see that there is an FID detector and an ECD detector, sorry. And in this case, because we have no specific flow information given, we would just use the maximum expected values for those detector types. Whereas on the right-hand side, we have information that this is an FID detector and we have specific flow information for hydrogen, air, and nitrogen makeup. So here we could be a bit more precise in understanding exactly what the detector flow rates are. So just to recap on calculating flow rates for detectors, first of all, count the number of each detector type. And remember that some GCs may have 2 detectors that are both operating at the same time and require gas, and add together the required flow rate of hydrogen, nitrogen, and zero air. If we don't have specific flow details, then we can just use the maximum expected for each detector type. We also have a GC gas calculator on our website, which you are free to use, which should help you to keep track of each GC's gas requirements. Okay, and now if we move on to carrier gas, then we would go through a similar exercise if you are looking to calculate the amount of gas required for carrier gas, as well as for your detectors. And to find the carrier gas flow rate, we would look at the total flow of carrier gas. The total flow is the total amount of gas flowing through the GC inlet. And this allows us to calculate the correct generator configuration to support a GC or a number of GCs within the same laboratory, and is a shortcut to calculating using split flows and the other information indicated in the acquisition data. Now, most GCs use a split or a splitless injector, and the calculation of flow rates will differ slightly depending on whether you're using split injection or splitless injection. But regardless of this, the best thing to do is to find the total flow, and this will give us the maximum amount required for that injector. Now, if you are considering using nitrogen or hydrogen for carrier gas, we would always recommend using either the nitrogen trace or the hydrogen trace, because these provide higher purity gas. So the nitrogen trace removes hydrocarbons from nitrogen, and the hydrogen trace has a dryer that provides slightly drier gas than our standard models. Remember that zero air can't be used for carrier gas supply. And as I just alluded to before, if you try to get into too much detail, if you're not used to looking at method information, it can become slightly confusing. So again, keep it simple and focus on total flow required for your carrier gas calculation. Now, if you have multiple methods used on a single GC, what you would need to do is just look at the method that has the highest total flow, so the highest gas consumption. And again, you should be able to find this from the method, either on the computer or in any acquisition data that's printed out. One point to note, if you are looking to convert from helium carrier gas to hydrogen, and you are using the same column, normally we would expect an increase in the amount of gas required of 25%. So if you had a total flow of 100 cc's per minute of helium, you would require 125 cc's per minute of hydrogen if you're using the same column. However, if you're converting to nitrogen, you can assume that the amount of gas would remain the same. So if it was 100 cc's per minute of helium, you could calculate with 100 cc's per minute of nitrogen. So again, if we look at acquisition methods, and again, normally there is an indication of total flow on the acquisition method. So here, for example, we can see we've got a total calculated flow rate of 287.34 millilitres per minute. So that is the total carrier gas requirement, or the total amount of gas going through the inlet. And then on the right hand side, in addition to this, we have the detector flow information. So we can see there we have, again, it's hydrogen. So here it is hydrogen carrier gas, and if we look at the hydrogen for the detector, for the FID, it's an additional 35 cc's per minute. So what we can do is take the total flow, take our detector flow of hydrogen and add those together. So we have a total hydrogen requirement of 322 cc's per minute. And then we would take our nitrogen and our zero air requirement, and that would give us our total amount of each gas required for this single GC system. So just to recap on calculating carrier gas requirements, get the highest total flow for each GC or GCMS, then count the number of each detector type and look at or calculate the total flows of hydrogen, nitrogen, and zero air. Again, if we don't have specific information, use worst case flow rates for the detectors. If it's the case that you don't know what your carrier gas flow rate will be, for example, if you're looking at a new GC system and you haven't actually established the method yet, it would be a good idea to look at other methods online to get an indication of the approximate flow requirements. But if you are in this situation, please do get in contact with the sales team at Peak, and we will work with you to look at what should be the appropriate gas generator solution for your laboratory. And so once we've got the total carrier gas flow and the detector flows, we add those together and we have our total gas requirement. Again, I mentioned a few slides ago, we have a GC gas calculator, which you can use to document all of the information from the GCs in your lab, and this will help double check that all the flow rates are correct and that we are looking at the correct generator solution for you. So a couple of points on helium conversion from to hydrogen. I'm sure that there may be some of you on the webinar today who are interested in this. We do have a number of pieces of information available on our website, but I just have a couple of slides on the key things that you need to consider before changing to hydrogen from helium. And we do, again, we have worked with a number of customers who have successfully made the change from helium to hydrogen. Key benefits being seen again in being able to move away from cylinder supply. There are other potential benefits with moving to hydrogen, such as higher throughput of samples. But we do make a number of assumptions if you are looking to move to hydrogen carrier gas, or if you have customers who are moving to hydrogen carrier gas. First of all, of course, you need to be willing, or your customer needs to be willing to make this change. It's important that you can change. So one of the considerations as well is that you need to check the methods that you use to make sure that hydrogen, or if you're looking to change to nitrogen, that these gases can be used for your methods, because some methods do not allow alternatives to helium. It's also to understand that it may take some time to convert the methods. So if you are reliant on the GC in your laboratory and can't afford any downtime, it may not be the right decision for you to make. So certainly this is a consideration that needs to be kept in mind. Normally, conversion can be done fairly straightforwardly, but it's important just to understand that there are some potential changes to the method that may be required that can be a little more time consuming. And this is particularly the case with GCMS more than GCFID and other non-MS detectors. And so this really feeds into the understanding the process of conversion. So again, if we are approached by customers to look at converting methods, it's important to read information on any of the potential pitfalls and expectations that you should have in the process of conversion. And again, we do have a lot of experience of working with customers on this, so please do reach out if you do have questions. In terms of online resources, there are 2 method translation options for you available online. There's one from Agilent and there's also one from Restec, both of which work in a very similar way, whereby you can input your current method parameters. So you can put in the carrier gas you're using, you can put in the column dimensions, any oven ramps that you have, and then you can put in the gas that you wish to convert to, and it will give you an idea of how the method will look, and you can change various parameters. So you can look at how much you can potentially speed up analysis. You can look to maintain efficiency and so on. So it's really worth exploring those bits of software if you haven't really considered changing carrier gas, but this is something you're considering. And then we also have a resource from Peak, where we have a list of methods where we've had customers who have converted from helium to either hydrogen or nitrogen, or methods where both options are available as alternatives. So please do look for this on the website. And again, when it comes to changing carrier gas, we do have a step-by-step guide to changing carrier gas, which is available on the website. We also have a number of application notes, so it would be worth looking at these if you're interested in this. So if you go to the Peak website and click on Discover, we have a number of resources. We have testimonials, blog pieces, and application notes available, which will hopefully be of interest, as well as all the information on our products. So just very quickly, looking at the precision range. So the precision generator range produces hydrogen, nitrogen, and zero air for carrier gas and detector supply. And it is a stackable and modular system. So depending on which gases you need or what your budgetary constraints are, you can actually buy individual components and then add to them as and when you are able. The whole range has extremely low maintenance, so it's annual maintenance across the entire range, with the exception of Precision Hydrogen and Precision Hydrogen SL, which will need a change of the desiccant cartridge on a periodic basis, depending on the flow rate of gas that you're supplying your FID detectors with. The cost of ownership of the generators is extremely low. So once you've made the investment in the generators, you should certainly see an improvement in your operational expenditure. The generators are designed to be easy to use. They're plug and play and can be installed very easily. However, if you do need assistance, then we have an extensive network of field service engineers who can assist you with this. And we can really configure a stack that should meet almost any laboratory's gas requirements. So again, please do look at the website and have a look at the products. And if you have any questions, we can assist you with making the right choice for your laboratory. Okay, so we are at the end of the slideshow. I think we have a few questions that have already been posted. So I'll just look at what's coming in. On the questions. Okay, so had a question about how environmentally friendly is a gas generator. So it will depend on a number of factors, really. I think one of the key considerations, as I mentioned before, is that a generator, once you've made that purchase and it's been delivered to your lab, will remain in the laboratory for the rest of its working life. Peak, as I said, have an extensive field support network, and we're able to get to customers worldwide to be able to maintain generators. So this means that you should not be reliant on repeat deliveries by truck of cylinder gas. All of the gas generators do require an electrical supply, of course. So if you are using a green supply of electricity, then again, this will improve the environmental friendliness of the gas generator. And the expected lifetime of a gas generator should be anywhere from 5 to 7 years plus. We do have customers who've had generators in their laboratories for 10 years plus. The main thing is to maintain them. If you're using a hydrogen generator, use good quality deionized water. And if you look after the generator, it should work for you for a number of years. Had a question on how long it would take to convert from helium to hydrogen carrier gas. So as I mentioned in the previous slides, this will depend on the method that you are looking to convert. And it will also depend on which detector you're using. Typically what we've found with customers is that for GCMS systems, it typically takes a little bit longer because it takes some time for the background within the system to stabilize if you're converting from helium to hydrogen. If you are investing in a new GCMS, it should be a little bit faster because you don't have any of the background that can result from having used helium. But for other setups, it can be as little as a couple of hours to just change the gas and move to hydrogen carrier gas. It's difficult to put a specific timescale on it, unfortunately. But as I said, we do have a number of application notes, and I think if you have application notes or other examples from of people who are using the same method as you, then this will help shortcut the process and should enable you to change carrier gas more easily. So the next question, somebody has asked, can they use hydrogen carrier gas if there's no written method? So normally if you are developing your own in-house methods, there should be no restriction in terms of changing carrier gas. Of course, this will depend on what kind of analysis you're doing and if there are any other measures in place that you would need to consider. So, for example, if you have standard operating procedures, you need to check if you're able to change these, and of course these would need to be updated. I would say that really there should be no restriction there, hopefully, but again, if you're unsure, then you would need to check with your colleagues before looking into this. And we have a question about how many GCs one generator can supply. So this will really depend on the gas flows that your GCs require. So for example, if you're just looking to supply a small number of FID detectors, and for example, you want to continue using helium carrier gas, or you're unable to change carrier gas, we can very quickly calculate with an approximate flow rate of 50 cc's per minute per detector that let's say a 200 cc precision hydrogen generator would be able to supply up to four GC FID detectors. So really, it would just depend on the flow rates required. If you're using carrier gas, as we went through in the example there, then it would be a case of looking at the total carrier flow and then adding any detector flows. And then we can look at the appropriate hydrogen gas generator. But we do have systems that can support or supply up to 1200 cc's per minute from a single generator. And we have a way that we can link multiple hydrogen generators together so that they can produce in excess of 1200 cc's into a single hydrogen gas pipeline. So that, I think, brings us to the end of the questions that I can see coming in. We'll just give you a couple of minutes in case there's anything else that you want to ask. Sorry, so one more question has come in asking about emission of hydrogen from the split vent and the safety of this. So yes, if you are using hydrogen carrier gas and you're doing split injection, then all of the split flow would be emitted from the split vent. So normally we're talking only maybe up to a couple of hundred cubic centimeters of gas per minute, which, if you think back to the example early on where we looked at the amount of gas contained in a cylinder, is actually a tiny fraction of the amount of gas in a cylinder. But if we were to consider a typical laboratory with a total volume of around 50 cubic meters, there's a threshold which is called the lower explosion level, and to reach this you need 4% of the total volume of your lab to be filled with hydrogen. So if we had 50 cubic meters, we would need just over 2,000 litres of gas. So if we are emitting only a couple of hundred cc's per minute, so that's 1/5 of a litre, I would say that the risk is very low in having a significant buildup within your laboratory. So normally we wouldn't expect there to be any significant risk of this amount of hydrogen being released. However, if this is a concern to you or to your health and safety team, then there's an option to vent the split vent to a fume hood, or you can also have an extractor over the top of your GC, which again would prevent any potential buildup of hydrogen. But I do really see this as a very low risk. But again, it is a consideration, so it's a good question. Okay, so well, thanks very much for the questions. I think there were some really good questions there, and thanks to everybody for taking the time to attend the webinar today. I think that brings us to the end of the session. So just like to thank you for attending, and please do look at the website if you need any information, and we will try to make a copy of this presentation available via Peak's resource space, so that you have a copy of some of the links to the information that was referred to today. Okay, so thanks, and have a good rest of your day. Bye.